I still don't understand this. Like, I didn't actually get to the AF. I actually did.
Okay.
It's 5.2.
Yeah. Okay.
Oh, what you can. It's so fun.
Okay. Can you show me the 15 tomorrow? Okay.
Won't fail.
Don't talk. I heard such lots.
This Oh, yeah.
All right, guys, page 40.
Yes. But. Yes,
Okay, we're gonna review from, guys. We'll review from last Friday. Just get some more practice with given the f prime graph. Can we sketch the f of x and the f double prime graph? Okay, so look at the f prime graph. Let's go ahead and label. Anything above means positive slope. Anything below means negative slope. Anything on the x-axis is 0. So keep in mind that this is not the shape of the original graph, right? Because this y-axis doesn't represent the position of the original graph. This represents now the slope value of the original graph. So I like to start off by creating a slope sign line as a bridge between my two graphs. Okay, what critical point can I place onto my slope sign line? Two. Okay, what's happening with the slope to the left of -4? Positive, right? I know it's decreasing. It looks like it's decreasing, but something else. Look at the location. Location is above the x-axis, so we know it's going to be different variations of positive slope between -4 and -1, below the x-axis, between -1 and 2. Yep, and then to the right. So you just want to sketch a graph that looks like this, right? So your relative max, relative min can be different y values than mine, but it just needs to show relative max at -4, relative min at -1, and relative max at 2. So I'm just going to arbitrarily choose a target point for relative max, target point for relative min, and target point for relative max. So relative max, relative min, relative max. Now, off the f prime graph, we can also gather information about the concavity of the original graph. So how do we find the points of inflection of the original graph if we're looking at the F prime graph? Good, the peaks and valleys, right? These are the POIs. My original graph. Okay. The negative slope of the F prime graph is going to correspond to what? A concave down of the original graph. Positive slope is going to correspond to concave up. Negative slope, concave down. Okay, points of inflection is at -2 and 1. Create our second derivative graph. And you know that your graph is going to become less and less, will have less and less curves, right? This is a degree 4, that's a degree 3, so this should be a degree 2, right? So we should experience less curves the more that we find the derivative. So point of inflection goes on the x-axis. Above is concave up, below is concave down. To the left of -2, I want the graph to live down here. Between -2 and 1, I want to have the graph live up here. And then to the right, below. Okay, fill out your characteristics. You can just pull all that from your 2 sign lines.
I don't know the Y value of the extreme.
You either I would give you information about it, or you can just make one up.
Okay.
Yeah, as long as, because if I don't give you any more detail, then your graph will still have the same relative max, relative min. It may be higher, maybe lower, and that's fine. Yes.
Would you rather us just make a Y value or just say like X equals -4?
I think on the test, I will give you some anchor points, and then from there you can just go from that point. Yeah, I'll give you some anchor points. And on the quiz review, on the test review, I'll give you some problems of ones, yeah, so you get more familiar of what the test could look like. Okay. All right, one more topic, and that's optimization. Okay, optimization is the process of finding the greatest or least. Either you're looking for the maximum optimal or the minimum optimal solution. For some constraint, which must be true regardless of the solution. Optimization finds the most suitable value for a function within a given domain. So here are the steps. You're going to write the equation for the variable you want to optimize. Substitute that equation down to one variable. And then you're really just setting f prime equal to 0. That's really the. Right, there's no, it's people sometimes connect it with related rates because it kind of has a word problem feel to it. But it's different in the sense that, yeah, there's no time involved, right? But the challenge, just like with related rates, is not with the calculus, it's with the setup. Once you can set it up and get your equation down to one variable, you just find the derivative and set it equal to 0. Okay, so let's look at some examples here. A manufacturer wants to design an open box having a square base and a surface area of 108 square inches. What dimensions will produce a box with a maximum volume? So if you see the word maximum or minimum or optimal, that's the variable that you're trying to find the derivative for. So using the variables that we see here, what's the volume of this box? Length times width times height, right? X squared H. Okay. I'll put a star next to this. This is what we want to find the derivative for, but we need some help because there's too many variables. So we want support from the surface area equation so we can make the proper substitution. Now, surface area is really just what the name implies. We're going to find the area of all the surfaces. Now, how many surfaces are we going to have here? Now, it's a open box. So how many surfaces are we going to have? 5. Yeah. So there's not going to be any material up top. It's just going to be material on the 4 sides and the base. So let's add up the area of each of the surfaces. Let's do the base first. What's the area of the base? X squared. X squared. What's the area of one of the vertical faces? XH. How many do we have? 4. So plus 4XH. Okay. Everybody okay with that? Okay, I can put this information in. 108 equals x squared plus 4xh. Or 4hx. Now, it doesn't matter which variable I replace, but we typically want to find the variable that's easiest to solve for. Which variable is easier to solve for in this one, h or x? H, right? H, this you gotta, it's harder with this one. Even if I could take out a GCF, I can't get that x completely on one side, so. Oops, sorry. My bad. I'm just dividing by 4x, keeping the h. Okay, make my substitution. And we should be able to get this all the way down to just rely on power rule. There's no need for product and chain and quotient rule. Clean all this up. Only thing we need is power rule. Okay, find the derivative v prime. Okay, set equal to 0. And solve for x. Okay, so the optimal size for our box is when X is 6. So it's asking for the dimensions, so we want the base length and width. We already have the X's, so how can we find the H value?
Plug it back in, Rich.
Yeah, plug into whatever the H equation that we found earlier. Okay, so pretty much for all these problems, we start off with two equations. One of them we're trying to find the derivative for, but we need a supporting equation to substitute into the equation that we want to find the derivative. Clean everything up, power rule, derivative set equal to 0, solve for X. Same process for if they're asking for the maximum or the minimum, it's the same process. It's just set your derivative equal to 0, solve for X. Yeah.
If you're
dv over dx, right? Okay, let's try number 2. Right, rancher has 200 feet of fencing to enclose 2 rectangular regions here. What dimension should we use so that the enclosed area will be a maximum? So we see that word, right? Maximum is describing area, so. Let me draw this diagram again. Okay, what's the area of this region here?
sure, that's fine.
Oh, 2x.
Yeah, so base times height, right? 2x times y. Okay, rancher has 200 feet of fencing. You know, that's something that has perimeter, right? So perimeter formula is just adding up all the sides. Make that substitution. Okay, I'm putting a star next to area because that's ultimately what I'm trying to find the derivative for. Is there one variable that's easier to solve than the other one? About the same, right? So I'm just always gonna, if they're about the same, I typically like to keep my x's. It's just more familiar to me, but it really doesn't matter. So I'm going to solve for y here, so I can replace y in terms of x. Okay, clean everything up. We should only rely on power rule here. There's no need for anything messier than that. Okay, once your area equation is down to one variable, clean it up, find the derivative, solve for x, set set a prime equal to 0.
Are we gonna have a calculator for step?
Yeah, calculator, yep. Yeah.
This X, like, never mind.
So it's asking for dimensions, so we just need to find x and y. Once I solve for x, I can plug into any of the equations that is solving for y here. Hey, page 45. Number 1 and 2, they're also area and perimeter, but the perimeter we're going to work in a cost. So I'll show you what that looks like. So page 45. Everybody okay so far? Okay, rectangular field is to be fenced off along the bank of a river. So we have no fence is required along the river. The material for the fence costs $8 per running foot for the two ends. So I'm going to call the horizontal the X and my vertical the Y. Okay, there's cost associated with our perimeter equation. So this is $12 for the side parallel to the river. And then $8 for the two sides. Find the dimensions of the field of largest possible area. We're trying to optimize area. So what's the area equation? X times Y. So no cost involved with area. Okay. The cost is not with what's inside here. The cost is with the perimeter, right? With the fencing. So let's do a cost equation. Now cost is pretty much perimeter involving perimeter and the dollar amount. So our cost is 12x plus what? 16. Yeah. And we have an amount to work off of, $3,600. So I can solve for one of the variables, plug in, clean it up, find the derivative, find a prime, set equal to 0, solve for x. So again, is there a variable that's easier to solve than the other? Not really. So I'm gonna always, if they're about the same, I'm always gonna target y. Just my preference to find the derivative in terms of x, but it's really up to you. Again, power rule is the only thing you need here. Okay, number 2. Okay, a rectangular storage container with an open top is to have a volume of 10 cubic meters. The length of a space is twice its width. Change that word there. So I know I have a relationship with the base here. One side is 2x, the other side is x. I don't know what the height is, so I'm going to have a different variable for that, h. Find the cost of material for the cheapest container. So the cost is not with the area, right? The cost is with the surface, area. Right. Sorry, the cost is not with the volume, it's with the surface area, right? That's the material that we're using to pay for, or it's the material that costs money, not the volume. So surface area of all the surfaces. Let's build that equation. This is an open top. Okay, open top. What's the base area? Squared, 2x squared. And what's the front face here? What's the area of that one? 2x times h. There's also one on the back. That's also 2xh. And what about the one on the side, the smaller one? xh. And there's two of them as well, right? Okay. Does that make sense? There's 5 surfaces at the base, the 2 larger panels, and the 2 smaller panels. And we can convert this into a cost equation. Material for the base is $10 per square meter, so I can take that 10 and multiply it into the base cost. And all the sides, it's all the same material, so it's $6 per square meter. So I can multiply that 6 into this equation or into that expression. Add the like terms here, 2, 4, 5, 6. Okay, so I incorporated the cost into my surface area. And it says, find the cost of material for cheapest container. So we're trying to optimize cost. Okay, but we need some help because we have a variable that's sticking out. So the volume equation will help us out there. We have volume is 10 cubic meters. Volume formula is 2x squared times h. Okay. Which variable would seem the easiest to solve for? H. Yeah, that h is by itself there. Okay, clean all this up, get it ready for power rule, find the derivative. Set c prime equal to 0 and solve for x.
About extraneous solution.
No, don't worry about that. No. Oops, x to the negative 1, sorry. Find the cost of material. So take this x, insert it into any of the cost equation. Guys, I'm only gonna put one optimization problem on your test, and it's gonna look like this one, so. We'll just focus our attention on that problem. Okay, any questions with any of the steps? Okay. Let's try one more here. This is number 3. This is a cardboard. Four equal squares are removed from the corners of all sides. Find the maximum volume. So imagine you have 4 corners that are cut out. And then the flaps will fold up. And then when the flap folds up, it turns into a box. So find the maximum volume. Well, initially, we start off with 15 by 10. But if we're going to cut corners out of each of the boxes, my dimensions will be different than that, right? So we know that this is going to be 15 minus what? If I were to cut the 2 corners out, 15 minus
2x.
x, yeah. And then this side will be 10 minus 2x. And what's the height of my box?
X.
Just x, yeah. So that x that I cut out will be the length of that flap, and that once that flap comes up, that's the height of the box. So this one doesn't require a second equation. We just FOIL all this out, power rule, find the derivative, solve for x. And sorry, this one does have an extraneous solution. The other ones we don't have to worry about. This is the only one. So this cleans up all the way to 150x minus 50x squared plus 4x cubed. Quadratic formula, we get 2 different solutions. Y is 6.3 out of the realm of possibility, but 1.962 is okay. 2 of those. Yeah, so I can't cut out that much material. Otherwise, I don't have enough to build a box. So yeah, 6.3 is too much. My width is only restricted to 10 inches on that side. Okay, so you guys have optimization homework tonight. Check your calendar. Tomorrow we'll do our quiz review. I'll give you guys a quiz review worksheet, and we'll have 2 days to go over them. Okay, go get your votes.